Our Introduction to Embedded Systems and Microcontrollers course uses a very hands-on approach to learning through integral labs and a term project. In this course, students are given a lab kit based on a breadboard and microcontroller and are tasked with constructing new circuits and developing programs to meet the specifications for weekly lab projects. The lab kit is shown here. It includes a breadboard, an 8-bit PIC microcontroller from Microchip, along with a PIC kit and circuit debugging and programming tool, wires, resistors, LEDs, push buttons and potentiometers, temperature sensors and phototransistors, a keypad, an LCD display, a servo and stepper motor, and components for providing power to the circuit. For each lab, students are provided with a circuit schematic and must construct the necessary circuit on their breadboards. Over the course of the quarter, students gain experience constructing circuits for many common embedded systems devices. Issues that students will inevitably encounter while constructing circuits and implementing their lab help to reinforce circuit design concepts and best practices. Students also develop troubleshooting and testing skills to identify the source of error in their project. The small portable lab kit allows students to carry their labs with them to work at home or in study areas on campus, and to bring their projects with them for office hour visits. This circuit is an example of one the students may construct. The program currently on the chip is for an early lab which utilizes just 2 push buttons and the 4 LEDs. The lab is called the Quick Reaction Game. The purpose is to develop a lab which will light the 4 LEDs in sequence and then provide a score based on how quickly the player presses the second button upon the 4th LED lighting. This lab provides an opportunity to present new concepts about timers and interrupts in microcontrollers, and most importantly, the need for non-blocking timing control, so that the program can respond to events such as button presses while providing precise timing control. Since this is a sophomore level course, students are still developing the skills needed for proper testing and verification of their circuits. One method of verification for the circuit would be to use an oscilloscope to measure the timing of the events and verify that the circuit is reporting the correct score. Students may find it difficult, however, to provide the proper stimulus for a complete test. This is also a challenge for grading the demonstrations, given the limited time I have for each lab group. I would like to put each circuit through its paces and test each boundary case, such as initiating a button press 1 millisecond after a timing interval. But try as I might, I'm just not capable of pressing a button at precisely 201 milliseconds after an LED turns on. To aid in the students' ability to verify their circuits, and in verifying demonstrations, we have created the tester circuit using the same components that are available in the lab kit. A general circuit was designed, exposing a number of I/O pins so that all the labs could be tested with the same circuit using only a new test program. The tester circuit connects to the student lab circuits and runs a program to put the circuit through its paces, testing each boundary case, and then reporting back a score or an error message in the case of a circuit which fails to meet specifications. Students have access to the circuit throughout the week, so they may test their circuit as many times as needed prior to their demonstration. Students at this level are also just beginning to understand how to develop a solution which meets specifications, and this device helps to identify cases where the circuit fails to meet specifications of which they were unaware. Here we see an example of a complete test being performed. Upon completion, the final score will be reported along with a code that may be useful for additional troubleshooting. Students are able to get instant feedback and may use this feedback to continue working on their implementation to improve their score. In the previous test, the initial score was less than the total points available, but through some tweaking of the time parameters, the score is improved to achieve full credit in this test. This past year was the first time I incorporated the testing circuit in the course. It's been an interesting addition and one that I think has the potential of being very beneficial for the students. There are still improvements to be made and a number of questions I'd like to address, however. The first is how to incorporate this into all labs, since some of the labs seem better suited to visual observation than a testing circuit. Another is how do I achieve the maximum potential of this device for helping students to develop their own testing and verification skills, so that they can develop the skills that we expect of our engineers in testing and verification of their own circuits.